Good morning. This is class 3 of the chapter Magnetism. Now, today we will learn about hysteresis. I think this you might have studied in lower classes about hysteresis, BH curve, etc. Okay, then, so I'm not going into much details, but we'll see it now. So, when a ferromantic material is subjected to a magnetizing field, magnetizing field means the external field that we apply. Okay, and if you are reducing that applied field to 0, then you are reversing it and then increasing it to an initial value, and after that you are trying to decrease it, then reverse it and again increase to its initial value. In that case, the magnetization of the substance returns to its initial value at the end of the process, and in this stage we say that the substance has undergone a cycle of magnetization. That is, you are having a ferromatic material, you are applying an external magnetic field. First, you are not, you are keeping the field 0, and then you are reversing it and then increasing, and it will reach a maximum value, and from that maximum value you are trying to decrease it, and again you are reversing the direction and again increasing to its initial value. So by doing this, we say that the material that we have taken has undergone one full cycle of magnetization. Okay. Now the magnetizing field H is varied with the magnetic flux density B inside the substance. So this magnetic flux density variation with the H is not linear, it will be in the form of a closed loop, just a hysteresis curve, right? So when a magnetic substance is subjected to a cycle of magnetization, it is found that B, that is magnetic flux density, it will always lag behind the applied magnetic field or the magnetizing field H. Now this lag of magnetization behind the magnetizing field is called hysteresis. This you might be familiar. This is a BH curve. It's nothing but a graph that shows the variation of magnetic flux density B inside the material, which is taken along y-axis, with the magnetizing field H, which is taken along x-axis. So a graph that shows the variation of magnetic flux density B within the material with the magnetizing field H is called BH curve. B is taken along y-axis and H is taken along x-axis. Okay. Now we are explaining it with an example. You are having a ferromatic material such as iron bar, and it is, first of all, you are not applying any field. So since H is 0, what will be the value of B, or the magnetic flux density inside the material? That will also be 0, and so that particular state is represented by the point O in the BH curve shown here. Okay. Now you are slowly magnetizing the field, that is, you are slowly increasing the magnetizing field H. Then now what you see, as H increases, B increases, that is, from the point O there will be a slight increase. That is, from the point O, if H is increased, B will start increasing this particular line, and it goes on increasing. That is, it is represented by the point, the curve OA, and after reaching the point A, even if you increase H, B, there will not be any increase in B. That is, the value has reached its maximum point, and that point is called A, which is called as a saturation point. Now after reaching the saturation point, what happens is that now you are trying to reduce H. That is, you are trying to reduce H. See the graph, you are trying to reduce H. So what happens to B? B also will reduce, and at this point, that is at the point C, the value of H is 0, but B is not 0. That is, even when the magnetizing field H is reduced to 0, the magnetic flux density B inside the material is not 0. That is, there will be a remaining magnetism in that material, and that is called residual magnetism or retentivity or remnants. Now you are reversing the direction. See, you are going here like this. You are reversing the direction, and you are increasing H, but in the reverse direction. Here B also increases in the reverse direction, and it will reach as a maximum value E, and after that there will not be any much increase. Okay, so you have reached a particular point E, which is symmetrically opposite to that of the point A. Now after that, see, this is a sentence. Now you reverse the direction of H, then H inside the bar vanishes, and so at a particular point, that is while you are reversing the direction of H, then the field increased for a certain value H, flux density inside the bar vanishes. That is, magnetic flux density vanishes. That is, this is a point. See, here we are reducing this H, and here in this particular point, at this particular point D, there is a value for H, but what is the value of B? The value of B is 0. So at a particular value of reverse magnetizing field, the magnetic flux density, that is B, vanishes, and that is called coercivity, and it is represented by the curve OD. Okay, so here this is the definition. The particular value of reverse magnetic field required to reduce the flux density to 0 is called coercivity. So you got two definitions: what is BH curve, what is retentivity, what is coercivity. Again, you are increasing the magnetizing field in the same direction. Then the flux density also increases in the reverse direction. That's the reverse form. Increases in the reverse direction. The bar again reaches the saturation point E, symmetrical to that of A. Okay, on reducing the magnetizing field H to 0 and then increasing in the positive direction, we again go back to the point A, and that particular full path is called hysteresis loop of BH curve. So this is one complete cycle starting from this particular point. Increasing reaches a maximum value and then it start decreasing, and this is a point called remnant magnetization. This is coercivity, and then it reaches another symmetrically opposite point to that of A. Again you are reversing the direction and this completes the loop. So this particular loop is called BH curve or hysteresis loop. So the material has undergone one complete cycle of magnetization, but in doing so, the energy that is spent for the material for magnetization will not be recovered when the material undergoes demagnetization. That is, there will be some energy loss, and that is called hysteresis loss, and it will be always in the form of heat. Now, hysteresis loop for soft iron is narrow and large, where hysteresis loop for steel is wide and short. So, in order to choose apt magnetic materials, we have to first of all study the hysteresis loop. Then only we can understand their properties such as retentivity, coercivity. So, this hysteresis loop actually help us to select suitable materials for making electromagnets, permanent magnets, etc. Now, materials for making permanent magnets must have high retentivity. High retentivity means they should have higher, they must last long, and it also must have high coercivity, and that's why steel is used for making permanent magnets, because steel has high coercivity and retentivity. So that is the reason why steel is used for making permanent magnets, and some alloys are also used, which is given here. And for us, whereas for making electromagnets, soft iron is used. Why? Because it possesses low retentivity and low coercivity. Next is Furry magnets. We know ferromagnetism arises due to the interaction between the spin motion of two neighboring electrons. Okay, now the spin alignment mainly depends on electrostatic energy. Now, if that electrostatic energy, if that favors parallel alignment, then and if it is of sufficient magnitude, then we call it as a ferromagnet. So for ferromagnetic materials, exchange interaction energy is greater than 0. So what are ferromagnets and antiferromagnets? So there will be two definitions. This is the definition for antiferromagnets. For an example, that is, in certain materials such as chromium and manganese, exchange interaction energy is negative. As a result, energy change favors anti-parallel alignment. Negative means anti-parallel alignment, and total magnetization will be equal to 0. Such materials are called anti-ferromagnets. So from here you can define what are ferromagnets also. What are they? Their exchange interaction energy is positive. As a result, energy change favors parallel alignment and total magnetization is not equal to 0. Such materials are called ferromagnets. So just study antiferromagnets definition and just reverse it, and then you will get the definition for ferromagnets. Okay. Now the material that has non zero magnetic moment in one of the directions are called Furry Magnets or ferrites. So you got ferromagnets, antiferromagnets and Furry Magnets. These are the definitions. Okay. Now the phenomenon of occurring spontaneous magnetic moment in materials is called ferrimagnetism. So there are four definitions: ferromagnets, antiferromagnets, ferrimagnets, then ferrimagnetism. Now some examples of ferrites are given here. Now ferrites usually have large saturation magnetization, and the resistivity is in this particular range. They are poor conductors of electricity and they are used for high frequency application. So this is the definition for ferrites, some of the examples and their properties. Now last topic is magnetostriction. It is nothing but the phenomenon of changes in dimensions of a ferromagnetic metal due to the magnetizing field. That is, when a magnetizing field is applied to a ferromagnetic material, there will be some changes in its dimensions. That phenomena is referred to as magnetostriction. Suppose that you have a ferromagnetic material, and if it undergoes changes in longitudinal and transverse dimensions, then that phenomena is called as Joule effect. Now if it exhibits a bending effect when a magnetizing field is applied, then it is called as Guilliman effect. Now when a magnetizing field is applied, if the ferromagnetic material undergoes a twist, then we call it as a Wiedemann effect. So three effects. Joule effect is actually the changes that occurs in a ferromagnetic material when a magnetizing field is applied. That is, the change mainly occurs to its longitudinal transverse dimension, then it is Joule effect. If it is a bending effect, then it is Guilliman effect. If it is a twisting effect, then it is a Wiedemann effect. So when applying magnetizing field, there will be some changes in the volume also. That is, there will be modulus of elasticity will also change. Sometimes change can occur in that way also. Now one use of this phenomena called magnetostriction is to produce ultrasonics of high frequency. That is, you are having a ferromagnetic material, and around that you are winding a coil carrying alternating current. In doing so, this ferromagnetic rod, it will expand and contract with a frequency twice the frequency of the alternating current, and finally it will start vibrating. And when this vibration of this longitudinal rod becomes equal to the vibrational frequency, that is, when the vibrational frequency, or when the frequency of vibration of this rod becomes equal to the frequency of the AC applied, then what happens? Resonance occurs. Then at resonance, amplitude of vibration will be maximum, and in this way ultrasonics of high frequency can be produced by using this rod. Another application is to make use of magnetostriction transducers. That is, for the manufacture of magnetostriction transducers. Transducer is a device which converts one form of energy into another. Okay, so these are the some of the few topics. So study the definitions. Now about Earth's magnetism we will learn in the next class. Okay, thank you.